So, not this part. Back up here. Slideshow. We'll be off. So, hello everyone. My name's Grady Connects, and I'll be running this course on algorithms and theoretical computer science. So this is the first session. We're going to be just talking about algorithms, what they are, a couple examples, just to get us familiar with the concept. So first, a little bit about me. That's me at age 4, grainy photo. I'm from Christchurch. I like computer science. I'm teaching a course for Sage. It's just about it. That's all that there really needs to be talked about for that. So also, if I scuff up a little bit, the Wi-Fi is a little patchy here, so it might freeze a couple times. Just tell me in the chat if that happens, please. I might be able to do something about it. Okay, so we'll start off with definitions of algorithm. Actually, first, does anyone have a definition of, I've already flashed it on the screen for like a minute straight, but does anyone have a definition of an algorithm that they think that they might have? Either a formal one or one that you've just got like through osmosis or from hearing it talked about in the media? I'll type it in the chat if you think you have one. No one, that's fine. That's like a process, kinda. Excellent. Could you elaborate? Because that's very much the right idea. Series? Fair enough. Anyone else also, aside from Jessica? Got an idea? Just type it in the chat. Or even say it out loud, honestly. It's fine if you just say it out loud. Some interactivity going on here. Give like a minute more for anyone who thinks they have an idea. Exactly. You're both very much correct. Okay, yes, now we're talking. Okay, people are talking. And I like especially what Evie said here. To make something happen, an algorithm has a point. It's a series of steps or instructions that causes something to occur. So let's see the formal definition, shamelessly screen captured off Google. An algorithm is a process or a set of rules to be followed in calculations or other problem-solving operations. But the way that we hear it mentioned these days is often in the context of a computer. So often you'll hear like about computer algorithms. Humans don't tend to do algorithms so much, but sometimes we do. For example, this Kraft macaroni and cheese dinner is really, if you turn it over, you'll see on the back an algorithm for the creation of a macaroni and cheese dinner, step by step, with a certain goal, which is the creation of a macaroni and cheese dinner. So yeah, that's really what an algorithm is. Some rules, some steps, however you want to phrase them, which have a point to them, and more often than not, in the context of a computer. Now, here's a little history related to the concept of an algorithm. It's come up a lot through time. It originated in, well, the first mathematical algorithm probably is Euclid's algorithm from ancient Greece, but the idea of an algorithm comes from long before that. It's such a general definition that it probably comes right back to the first time someone made fire. Oh, here we have someone else. All right, welcome to the new, I think 2 people joined in the last couple minutes. We're talking about algorithms, and right now we're talking about some of the history of the concept. So some of the first actual formalizations of the idea of an algorithm came long after the time of ancient Greece, and I believe around the year 1000, I might be wrong about that, with this fellow here, very intelligent. He gave the name to the idea of an algorithm, but he also gave the name to the mathematical field of algebra with a book he wrote called Algebra, which got slowly mutated into the modern name algebra. Then after that, we've got Ada Lovelace, there wasn't really that much progress on the conceptual idea of an algorithm since this fellow all the way up to the mid 1800s when we had, it might not be mid 1800s, it might be 1700s. I am honestly not too good with history. I'm a computer guy. But Ada Lovelace was one of the first computer programmers, and there's probably going to be a stage session named after her at some point. She's widely considered to have written the first computer algorithm ever created. Uh, yes, exactly. Charles Babbage, he was the hardware guy. He created the difference engine, which was like the hardware on which the algorithm was to be run. Or more precisely, he never actually managed to create it, which is very unfortunate, but he made the plans for it, and she made the algorithm that was going to be run on it. She was also the daughter of Lord Byron, the poet, which is pretty cool. Lots of interesting coincidences in history. But after that, it was a long time coming until we had Alan Turing in the 1900s. His is a very famous, very sad story, but with algorithms, he formalized the idea of an algorithm, really got it down to a science. He created the idea of a Turing machine, which is like a simplified representation of a computer, is a way we can think about it, to run algorithms. And this idea of a Turing machine helped him to solve many problems, including many famous outstanding problems related to algorithms, including the halting program. Admit this person. I will type that in the chat, halting problem. This is a pretty cool problem, and if anyone wants to look into it in your own time, it's pretty cool. I sent that by direct message by accident. Okay. Everyone in the meeting. Halting problem. Anyway. So Alan Turing formalized this idea on normal computer, and now by his time we actually had normal computers, so you could run and test algorithms. And then process was pretty steady from then on. Many new and different algorithms were created to solve a variety of new problems that the new ages and millennia brought up until the creation of quantum computers. Who's had, just out of interest, who's heard of a quantum computer? Thumbs up, maybe. Yeah, we got some thumbs up. Four. Five people have heard of a quantum computer. That's good. We don't really need to know about quantum computers for this session because like they're really, really, really complicated things. But basically they're a more advanced version of a computer. And Shor's algorithm, keep doing that. Shor's algorithm is one of the most well-known algorithms designed to be run not on a classical computer, but on a quantum computer. So these four are some of the biggest figures, biggest names in the history and development of the concept of an algorithm. Right up to the present day, as you can see, this is a color photograph. This fellow is still alive. So it's very much a new, exciting, and still broadening field of development. Anyway, so enough talk about algorithms. Let's do an actual algorithm. Say you have a collection of numbers. For example, I don't know, you've got a bunch of different strawberries in a box and you want to find the weights of the different strawberries in the box and you want to find the heaviest strawberry. One way that you could do that is to perform this algorithm, which is basically you create a variable being like just a little, say you write it down on a piece of paper, the largest strawberry you've seen so far, and then you roll through all the strawberries, and if any strawberry you find is bigger than the biggest one you've seen so far, then you write that weight down. And at the end of it, the last number you've written down will be the answer. And the reason why that works is because at some point there will be a biggest one and you'll write it down, and then after that you won't write anything else down. So that might have been a little poorly explained, but do we all get that? It's like, it's an algorithm in a sense. It seems almost a little too simple to be an algorithm because like it's doing something, it's not like solving a quantum problem or finding a Google Maps route or curating your Instagram feed, but it's most definitely solving a problem. So it is definitely an algorithm. So is everyone good with that? Using the thumbs up feature a lot today. Lots of thumbs up. Is anyone not good with that? That's a better way to do it, in my opinion. People seem to be good with that. That is good to hear. It is very good to hear. Okay, yeah, so this is like, it's an explanatory example. And the reason why it's an explanatory example is because it can tell us a lot about what an algorithm, what kind of processes might underlie more important algorithms. For example, this algorithm can't be applied to just any old collection without a way of comparing items. For example, you can't find the biggest number in a box of strawberries. You can find the heaviest strawberry, so probably not a good example for me to use as my first example. You can't find the biggest number. They're strawberries, they're not numbers. So there are some inputs that are allowed for this algorithm, and there's some inputs that aren't allowed. Also, for example, if you had a collection of numbers with more than one instance of the biggest number, say several different strawberries all of the same weight, this wouldn't really work because you would just say, oh, this is the biggest weight without finding which elements they were. If they're distinct in some way, but they all have the same weight, for example, one strawberry is redder than the other, but they all have the same weight, then it won't get you all the strawberries, it'll just get you one of them. So you've got to be very careful about how you apply algorithms. So the ideas underlying this whole thing are the algorithm was written out as a sequence of instructions. Notice it was written to perform the algorithm, you do this, then you do this, then you do this. Some inputs weren't allowed. For example, the box of strawberries or a box with multiple different equal items. You need a defined way to compare different elements. And finally, we use two different common computer science concepts, loops and indicator variables. So this part here is called a loop. We went through everything in a collection one by one, looked at them all individually. That's called a loop. We looped through the collection. And an indicator variable is like this thing x here, where we store something that we've seen or some computation on something that we've seen. Just a little, like a little notepad that we wrote something down on. That's like an indicator variable from the ground up. Anyway, that one's kind of a little too basic to talk about because it's like finding a big thing in a bunch of smaller things. So let's look at something that's a little more complex. So who's heard of a GCD? It's a mathematical concept. Who's run into it before? Couple hands up, that's good. But you don't really need to know about the GCD to understand Euclid's algorithm. So basically the way that a GCD works is it's the biggest number which divides two different separate numbers. For example, oh, and by the way, what it means by divides is if it's a factor of those numbers. For example, 7 is a factor of 21 and also of 49. 3 is a factor of 21 and also of 9. A number divides another number if it's a factor of the number. So the GCD is the biggest number, which is a factor of both numbers. For example, the GCD of 21 and 9 is 3, because 3 divides 21 and 3 divides 9, and try as you might, you will not find a number bigger than 3 that divides both 21 and 9. So finding GCDs can be very useful in a lot of different computer science applications, as well as in just pure number theory applications. Lots of people in this lesson. It can be useful in a variety of different ways, but one thing that's very useful is to be able to calculate it quickly. And so here's an algorithm that can perform a GCD. It's called Euclid's algorithm after this fellow here, Euclid of, I believe, Alexandria, and it's been around since antiquity for a very long time, a couple thousand years. So here's the way it works. And I feel like this would be actually really a lot better explained with a couple of examples. A lot better explained with a couple of examples. So to perform the algorithm, what we do is we check first up if, so wait, sorry. Getting ahead of myself. So the way it works is we take two numbers, A and B. Take two numbers, A and B, and we want to find the GCD of them both. Now, Euclid's algorithm revolves around this idea that first up we check if B equals 1 or B equals 0. B equals 1, then we can use the mathematical fact that the GCD of any number A and 1 is always equal to 1. And if B is 0, we can use the fact that the GCD of A and 0 is always equal to A. So these are two mathematical facts, and you can convince yourself of why they work. The first one here works because 1 only has 1 as a factor. And the second one here works because 0 has every number as a factor, because 0 can be written as, for example, the GCD of 3 and 0 equals 3, because 0 equals 3 times 0. So first up, we check if one of those special cases holds. But if it doesn't hold, then we move ahead and we perform the algorithm, the central step of the algorithm, which is say that the GCD of A and B is equal to the GCD A and A minus B. Now, what we do here, by the way, very important, we always make sure that A is greater than B first. If not, we just swap them around, we interchange them. It's a bit glitchy. That might just be me, like, speaking poorly. When you say it's a bit glitchy, what are you experiencing? Like, is it pixelated? Are the noises jumping up and down? Lag. Okay, just a moment. Give me 1 moment. My sister was microwaving nachos. Great fun. So that would explain some things. Okay, let's do this from the start because I don't want anything. Yeah, I know, right? Uh, I don't want anything to be missed here because this is a very, very good explanatory example. So from the top, yeah, but nachos are good. Nachos are good. Nachos are worth it. So from the top, the GCD of two numbers. So the GCD is a mathematical concept. Basically, when you have two numbers, let's call them A and B, the GCD of those numbers is the biggest number C, such that C divides A and also C divides B. And there's no number bigger than C that has those two properties. So what we mean by divides, by the way, if anyone needs a quick refresher, is, for example, 7 divides 21. A number divides another number if it is a factor of that number. If the second number is a multiple of the first, or for example, 4 divides 8, because 8 is 2 times 4, and because 21 is 3 times 7. So yeah, basically that's the definition of what it means for a number to divide another number. Now this GCD concept might not seem very useful, but it can actually be very useful. It underlies, for example, encryption, which is helping to encrypt this call and make sure that no one can just snoop it on your Wi-Fi. Not sure why anyone would want to snoop this call or look into Euclid's algorithm, but if they wanted to spy on us, they could, but not with encryption. And GCD is a central step in mathematical algorithms that are used to encrypt data in your Wi-Fi. So it can be very useful sometimes. Now, basically, well, one quick example, the GCD of 21 and 9 will be equal to 3. Because 3 is the biggest number that divides 21, because 21 is 3 times 7, and also 9, because 9 is 3 times 3, and there are no bigger numbers that have that property. No bigger numbers that divide both 21 and 9. You can check for yourself if you want, but no such numbers exist. Am I? Yes, I am typing. Oh wait, that's very unfortunate. I'm not sure what's up with that. Give me a second. Okay, that's very unfortunate. That would explain a few things, actually. That would explain quite a few things. Share screen, and I will just share the entire screen. Okay. Who can see this? Can you see this? Some thumbs up. Okay, I think this is going through now. Yeah, that would be very unfortunate if you couldn't see any of the stuff that I was typing. That would be very unfortunate. Sorry about that, guys. First time on this platform. Okay. So the GCD of 21 and 9 is 3. That's unfortunate. No one saw what it was. But is anyone Yes, I was typing a little. Yeah, it's a bit unfortunate. I wasn't typing anything of much import though, so it doesn't really matter. So anyway, Euclid's algorithm, we compute this GCD. The whole point of Euclid's algorithm is to compute a GCD. A greatest common denominator, by the way, is what the big acronym stands for, greatest common denominator. So enough about what the greatest common denominator is. Here's how you perform the algorithm. It centers around a mathematical fact that says that the GCD of two numbers, a and b, is equal to the GCD of that number, the first number, a minus b, and the second number as it was. So this might look a little confusing, might look a little daunting, but it's it's mathematical facts, and you don't really need to know too much about it to use Euclid's algorithm yourself. And that's the beauty of it. You don't need to prove any of the stuff to use it in an algorithm. So anyway, it revolves around that idea. It also revolves around two other mathematical facts, which first one is that the GCD of any number in one is one, and the second is that the GCD of any number in zero is the first number. So if you want a little challenge, you can try and prove all these three things. They're interesting little exercise to the reader, but it revolves around these three ideas. So to perform the algorithm, first thing you do is you check if one of the two numbers that you're trying to perform the algorithm on is 1 or 0. And if neither of those things hold, then you perform the algorithm on this, on the second pair, b and a minus b. So I've said perform the algorithm quite a few times. So the idea here is just that performing the algorithm involves performing the algorithm as a sub-step of performing the algorithm, which is a bit weird. It takes a little getting used to. But it will hopefully be cleared up a little by an example. So can anyone give me a number? Number in the chat, random number. Hopefully not too big. 18, great number. 62, also great number. Okay, 18 and 62 we will use. 4 is also a great number, but 4 would make it too easy because 4 would be over in like half a minute. So 18 and 62. 18 and 62. So first up, so what we want to do is we want to find the GCD of 18 and 62. And the way that we're going to do this is first we check, is 18 1 or 0? No, it is not. 62 1 or 0? No, it is not, as it happens. So we shall carry on from here then, and to perform this step. First we find the bigger of the two, it's 62, just to make sure all our numbers stay positive. It's always useful for things to stay positive. 62 is the bigger number, so we will now replace this with the GCD of 18 and 62 minus 18. Now I'm no mathematician. What's 62 minus 18? It's like 52 minus 8 is 44, I do believe. Yep, okay. So this is equal to the GCD of 18 and 44. Now we're going to do it all over again. Is 18 1 or 0? No, as it happens, it is not. Is 44 1 or 0? It is also not. So we shall do it all over again. We take the difference of the smaller number from the larger number. So 44 minus 18, again, quick mental math stuff. It's going to be like 34 minus 8, which is 26. And we're going to do it all over again. It's 18, 1 or 0. No, this might get a little repetitive. The 26 is also neither 1 nor 0, so we're going to do it again. GCD of 18 and 26 is equal to itself, the GCD of 18 and 26 minus 18. We take off the smaller number. What we get is 26 minus 18, which happens to be 8. And now, caution, we can't just keep subtracting off 18. We've subtracted off 18 like 3 times in a row now. We can't do it again. Because while neither 18 nor 8 is 1 or 0, now 18 is the bigger number, and 8 is the smaller number. So this time we're going to take the 8 off the 18 instead of the 18 off the 8. And we're going to get equal to the GCD of 18 minus 8 and 8. 18 minus 8 will be 10. Now we continue on. This itself, at this point, I've done it like quite a few times. Who knows what the next step is going to be? You guys, too good. Absolutely too good. Neither of them are 1 or 0, of course, so we go to 10 minus 8, which is 2, and we keep the 8. Now, again, 2 and 8. I'm just going to speed through this last bit. None of them are 1 or 0. We'll stop when one of them is 1 or 0. It's equal to the GCD of 2 and 6, which is equal to the GCD of 2 and 4, which is equal to the GCD of 2 and 2, which is equal. Now that they're equal, we can take either one to be the bigger number, which is equal to the GCD of 2 and 0. Now, one of them is 1 or 0. So we look back. The GCD of A and 0 is A. So the answer is 2. And the GCD of 18 and 62 happens to be 2. And I claim that you can try as hard as you would like, but you will not be finding a larger number than 2 that divides both of those numbers. So yeah, you guys catching on very well. Looks like you understand your stuff. So I will now pick myself. Yes, that would be funny. And that would ruin my day. Man. I will now pick myself 2 numbers, and neither of them will be prime. I will pick the number 15, and I will pick the number 25. And now, let's see who's going to be the first to type the GCD in the chat. Speedrun, who can do it? Too fast, too fast. 2 people. Okay. Very nicely done. Let's do it again. 18 and 24. Too fast again. This time it's not the same 2 people. It's, oh, everyone's doing it. Nice. Very nice. Everyone's jumping on the GCD of 18 and 24 train. Love it. Love to see it. So yeah, the way that you would solve this now, there's not a y in it. There is no y in it. How would you do this? Without just going on Google, because I know someone's going on Google right now. Yeah, this one. This one. I hope not. No, neither of these are prime. They're both even. Yeah, all yours. So how would you do this? I don't actually want anyone to do this. I hope no one is like Googling this right now. How would you perform this operation? Oh man, you guys, too much. Wow. Yes, you will not pray God will tell you the answer, though that might be pretty effective. You will use Euclid's algorithm. Yeah, the same method as before. Euclid's algorithm will be pretty long-winded if you try to do it on your own. Yeah, the first one minus the second one. This could take some time. In fact, this will probably take a lot of time. This would take the entire meeting time and then some. So we are not going to be brute force calculating this, unfortunately. What we will do is maybe let a computer do it for us. I'll leave these numbers here, just leave them around. Yeah, if you see this on a test, just skip it, go to the next one. And speaking of going to the next one, I'm now going to go to the next one. So the ideas underlying this algorithm, again, was written out as a sequence of instructions. In this case, this one was like too simple to even need any mathematical basis. But in this case, this idea down here, this big equation down here, was used to make it all work. That one and the other two, that GCD of A and 0 was A, and GCD of A and 1 was 1. So some theoretical math was used to make it work. You don't need to understand the theoretical math. It's fine if you don't, but it was what was used kind of under the hood. In the same way that you don't need to understand how the engine works to drive a car, you don't need to understand the theoretical math to run an algorithm or even to write your own algorithm. So the algorithm was written as a sequence of instructions. Theoretical math was used to make it work. A couple inputs were not allowed. I didn't really go into too much detail here, but Euclid's algorithm cannot be performed on 0 and 0. It's just not possible. You just can't do it. It's very unfortunate. Because the GCD of 0 and 0 is undefined. The reason why it's undefined is because like all the numbers divide 0, but all the numbers also divide 0. So like it could be just as big as you want it to be. Some little noise keeps occurring. I think it's the Sage server. I'm just going to take one moment to rid myself of that. Site. All right, back to it. Don't want you guys distracted by some little pinging noises. So there's a lot of theoretical ideas underpinning this Euclid's algorithm that we can apply to other algorithms, and we will apply to other algorithms. We'll keep coming back to these central ideas that an algorithm is written as a sequence of instructions, that theoretical math helps us to make algorithms work and design algorithms ourselves, that some inputs are disallowed from algorithms, sometimes you just can't apply it, you have to have inputs of the right form. In this case, for example, if I asked you to find the GCD of bananas and apples, you might have some difficulty. And finally, this thing here. So in the previous one, we used loops and indicator variables. I have no laser pointer. Here's my laser pointer. In the previous one, we used loops and indicator variables. In this one, we use something called recursion. So recursion was this idea that to perform the algorithm, we simply perform the algorithm. And amazingly, that actually worked. That didn't break our brains or throw any logical errors or whatever. To perform the algorithm, you just perform the algorithm. Recursion. So recursion is more formally the idea that something can, as a subtask of an algorithm, as one of its steps, it can be to perform the algorithm, but it has to be on some smaller input in some way. For example, here was b and a minus b. So together, those are kind of smaller in a way. You will have noticed that when we were doing the explanatory example, the numbers just kept decreasing. They never went up. And that's for a reason. The recursion has to terminate. It has to end somewhere. Otherwise, you'll just be calculating numbers until kingdom come. And at that point, you really should just, like one person said in the chat, you really should just ask God to help. Yeah. So you got to make sure the recursion terminates. So these are a few of the ideas that underlie algorithms in that case, but these are some boring, kind of musty old Byzantine algorithms. There's some more interesting algorithms that we see all around us and might not even notice they're there, but they're always operating. For example, social media algorithms. If you have Twitter, or if you have Instagram, if you have any media, yes, stock market algorithms, that's another one. So anyway, social media algorithms, if you have any media, you have almost certainly run into these. They will curate your feed, they will make content for you, they will do just about anything in this day and age. Social media algorithms basically are the engines that run social media and make it a pleasurable viewing experience for you and highly addictive. So anyway, enough about that. Google search algorithms. We might actually, if we have some time, we might cover how Google search ranks pages, which is a very interesting algorithm and surprisingly not too complicated. Like you would think it's 50,000 pages of code all going into real depth on some ridiculous thing, but no, it's a lot simpler than you'd expect. But yeah, Google search, every time you make a Google search, and there are billions made each day, every time you make a Google search, some algorithm somewhere is being run in some submerged data bank somewhere in California. It is being run. Pathfinding algorithms, whenever you're going somewhere, use Google Maps or use Apple Maps if you're so inclined, you can run into an algorithm. In this case, you'll most often be using some variant of an algorithm called Dijkstra's algorithm or Bellman-Ford, which we will run into both, probably more Dijkstra's, but we will run into both along the path of the next few lessons. Machine learning and AI, that's an interesting one, and one that you will almost certainly hear more about if you stick around with Sage, because I believe there were a couple courses taught in previous sessions, and I believe there will be future courses taught on those subjects, because they are subjects that are endlessly growing and endlessly becoming more relevant. And data mining algorithms, data mining is basically you have a lot of data, you want to find patterns in it, and the reason why you want to find those patterns might be good, you might be trying to save lives by finding the optimal allocation of resources in impoverished countries in Africa, or you might be trying to make a lot of money by figuring out what ads people like. And you've got a lot of data on what ads people click and they don't, and you want to find what patterns you can find in that. And there are algorithms to find patterns in that data. And finally, yes, stonks, there's stock market trading algorithms that can make you money. What kind of code? What the stuff that comes up honestly isn't that good. That is true, mostly due to the fact that we are still in the dawn of the age of algorithms. It's not all figured out yet. The very fact that an algorithm can guess even slightly what kind of stuff you like is almost scary. An algorithm can simulate the human brain, the most complicated computer on the earth. An algorithm can simulate it well enough to figure out that if you're more into cats than dogs, it will probably be able to figure that out. And in fact, The fact that the stuff that comes up honestly isn't that good, I'm not so sure about that. Recently, there was a big thing in the news about, oh, what was it? Target figured out from some unfortunate person's purchasing habits that they were pregnant and figured it out before their family did and started recommending them like pregnancy products and figured it out before the person themselves figured out they were pregnant. Yeah, it's a lot better than you might expect. Really, a lot better. I'm not sure how it did it. I'm really not sure how the algorithm pulled that one off. Yeah, and then Netflix goes and like recommends you Shrek or something. I don't know. I don't know. So sometimes they're really good and sometimes they're bad. But anyway, we're getting off topic here. What kind of code was used to make Google? I am honestly not sure. Are you asking like what kind of coding language or what kind of like algorithms we used? Because the algorithm is called PageRank, not after web pages, but after Larry Page, founder of Google. Coding language. Oh, honestly, I'm not sure. That is a question for Google. Put the Google algorithm to work to tell you about the Google algorithm because yeah, I'm not quite sure. That's an interesting question. An important point to ask though is that the coding language, an important point to set is that the coding language doesn't really matter when you get right down to it. Any coding language is fine, except for JavaScript. But aside from JavaScript, every single coding language can probably express the same stuff. Almost all languages today are what's called Turing complete, meaning that they work. You can write algorithms in them. Why not Java? No, sorry, that bad joke. JavaScript is like really bad for coding, and it can be difficult to code in. Bad joke, sorry. Um, yeah, they might have even used a little JavaScript. Yeah, I'm pretty sure that Minecraft coding language is Turing complete. I might be wrong about this, but I think it is Turing complete. So if you want to go and implement Dijkstra's algorithm in Minecraft, go ahead. Knock yourself out. But anyway, these are some of the more interesting algorithms that you find around you every day, but I feel like it's worthy of mention, a very, very honorable mention, the not so interesting algorithms, because there are a lot of them. Algorithms that program, for example, does anyone have a Roomba? I've never actually met someone with a Roomba or like one of those robot vacuums. Does anyone have one? Raise your hand. Nobody has a Roomba. Someone has a Roomba. Two people have a Roomba. Oh, it's one person putting up two hands. Okay, very nice. Good to hear that someone does actually have a Roomba. There are algorithms that will make your Roomba work. It will tell it how to move around. And it might seem silly, but there are so many different algorithms. Yeah, the Roombas are kind of dumb. A lot of the algorithms that are dishonorably mentioned here are kind of dumb, but the point that I'm trying to make is that there are a lot of these big flashy algorithms that you will hear about in the news and you will hear about all the time, and you will hear about in courses like these. But there are also less flashy algorithms. There is also a new person. Oh no, an old person who disconnected and came back. But there are less flashy algorithms. They do exist and they manipulate all the stuff around you, all the data around you. There are even algorithms that you execute yourself. Call back to that pasta recipe. So yeah, anyway, those are some of the more interesting algorithms. So one question, though, is how can we display these algorithms? And one way that you can do it is a flowchart. Flowcharts, like, who's seen a flowchart before? Probably a lot of people, right? Probably a lot of people have seen a flowchart before. They're pretty ubiquitous. You see them all the time in like graphics, stuff like that. Basically, the way a flowchart works, if you haven't seen a flowchart before, is you start somewhere. In this case, you start at the point marked entry. The entry point, nope, not that. The entry point, and you go down, you follow the arrows, and whatever is in the box, you do that. So here it says you take A and B as input. That's pretty cool. You take A and B as input. Now, next up is like a little node just to make it all look good. Next, you check if B is 0. In this one, they don't actually check if B is 1, and you don't necessarily need to. In fact, yeah, you don't necessarily need to check if B is 1 for the algorithm to work. So they check if B is 0. If it is yes, 0, then they go all the way down and print A, and that's the way that you end it. And if it isn't 0, follow the arrow that says no. Check if A is bigger than B. this is just to make sure that all the numbers stay positive, as we did before. We always used the bigger number and took away the small number, like 10 minus 8, instead of 8 minus 10. And they went to, and then you subtract off the number. If A is not bigger than B, if A is less than or equal to B, you take A off of B. If it's bigger, you take B off of A. And then you go back up this little black box and you do it all over again. You just keep going. Notice that underneath all this, the underlying structure is that of a loop. You go around and around and around. And that's recursion. That's how you display recursion in, well, really, that's how you display an infinite loop. You can formulate algorithms. It's worth noting here that you can formulate algorithms in a lot of different ways. You can write them down differently. You can write them down with recursion, the way I did, or you can write them down with a loop, the way that the first one was done. In this case, they've written the second algorithm, which was written down as recursion, as a loop. And oftentimes you can do that. Sometimes you can't, but that's completely a story for another day. There's a much better way to display an algorithm. It's a little harder to read, but it's a much better way to display an algorithm. And it is, in this case, I'm using Python. I'm not using JavaScript, but a much better way is to display it with what's called a programming language. So what year level is this needed? I'm trying to do it from the ground up, like year 8, 9, and the reason why I'm trying to do that is because everyone here could be at like different year levels. But if you think I'm going too high above, absolutely tell me that and I will cut it all down. I'll cut out like some of the weirder slides or whatever may be. I'm year 13 myself. The year level needed to understand this should be year 8, but I am not so good at teaching, so it might not be year 8. Yeah. Are you asking this question because, yeah, year 13 represent. Are you asking this question because, like it's too hard? Because if so, tell me immediately. No? Oh, in a test. Oh, well, the day that you will expect this in a test, this is a great success. This is a great success. Congratulations to you, man. Well done. The day you will expect this in test is probably, okay, if you've ever done a computer science competition, you will use some of this stuff. However, the day that you will expect algorithms and the stuff we're going to cover in the rest of this course in a test is university, if at all. You will never need it in, like, if you don't want to show off to your teacher, you will never need it in high school. And like Dijkstra's algorithm, that's a name I keep dropping, and it's for good reason. It's a very cool algorithm. Dijkstra's algorithm you will not be needing until, yeah, until like university. Definitely university. However, as soon as you enter the workforce, if you decide to go into coding, I don't know why you would, but if you do, because coding sucks, but if you do, you will start needing them so much more. Euclid's algorithm, Dijkstra's algorithm, all these algorithms. Yes, I did, and I'm one of them. So I'm sure it's fine. Yeah, Euclid's algorithm and the algorithms we will go into later, they will be useful to you in the far, far future if you decide to make that your career path. And even if not, it's always nice to understand what's going on behind the black box. Anyway, what we have here is, hopefully not a failure to communicate, what we have here is a Python script. And this is Python. These red things are errors from something I tried to do earlier today. We will not have any errors. We'll go to idle. We'll open it up. Idle is like a thing that does code for you. It's very cool. So what we're going to do is we're just going to type all this in because I am foolish and made it an image instead of, but actually this is a teaching moment because I can explain each line. So diff Euclid each GCD AB. What this means is basically just we're defining a function. And what the function is going to do is it's going to take two numbers called A and B, and it's going to find the GCD of them, and it's going to give that back to us. So this is just an implementation of everything we've been talking about for the last like 4 slides. So first up, we check if A is 0. And if A is 0, then we can return B, because B will be the non-zero number, and we'll give that back. We're assuming that they're not both 0, because then it's undefined. In fact, I will show you that later. If I try to give it inputs of 0 and 0, it will break down. It will not work. So if A is 0, we return B. And if b is 0, we return a. And in this case, notice this. Before, I said that we check if b is 1 or b is 0, but in the Euclid's algorithm flowchart, we didn't actually check if b was 0. If b was 1, we only checked if it was 0. And we also in this code, we're not checking if it's 1. So, sometimes there are different variants of the algorithm. The important part is that they all work. Anyway, let's bring this back. A is bigger than B. So here, we want to make sure A is bigger than B. The reason why is because we're going to be taking B off of A, right? So we want to not have any negative numbers. And in fact, if you try to put negative numbers into this thing, it will collapse. I even wrote that at the bottom. It only works for positive integers. It will just completely collapse if you try to put in negative numbers. So we return the Euclid GCD of A minus B and B. And otherwise, the else here stands for like otherwise. If else, so if this holds, then you do something. Otherwise, we're going to do something else. And the other thing is, okay, A wasn't bigger than B. That means A is less than B or A is equal to B. In either case, we can do the GCD of A and B minus A. Nice, very nice. And now we'll save that as my code thing.py, and we're going to press the run button. Very cool, it will do the code for us. And now we're going to pick, well, 18 and 24, they got a big audience response, and it gets 6. Good on you. And now, I'm not actually sure how fast this algorithm is. I've done it with like big numbers before. Academy? Oh dear. That's some spicy stuff someone's doing. Wait, me? Oh no, not that. That's just a thing. I thought someone was talking about it in the chat. Use the weird numbers from earlier. Yeah, I'm looking for them now. Oh, here we go. Someone was blocking off my taskbar, but here we go. Here we go. Now we're going to see. Now we humans, we are foolish and weak mortals. We cannot hope to do these massive numbers in our heads or even with paper. It would take years. But a computer can also not do them because they are so big. That sucks. Man, what the? Okay, some slightly smaller number spams. Yeah, that really sucks. I outdid myself by writing 2 massive numbers. Okay, in this case, it gets 1. As you can see, some large numbers. It's a real shame. It's a real shame. It just completely collapsed. These are also 1. GCDs do tend to be 1. I will make this decidedly not 1 by ending it with a 6. Okay, we're done here. Yes, I tried to use even numbers. Very unfortunate. And this is something that will happen. Yes, Hazel, honestly, I'm going to have to go with your path at this point. I feel like these numbers are just too big. Yeah, that was rather embarrassing, but it's a learning moment. And the learning moment here is Euclid's algorithm is good, but it's not that good. It's not that good. And God probably does have some better things to do than solve my massive numbers problem. So Euclid's algorithm, it can be good, but it's not that good. But are there better ones? And more importantly, what do I mean by better ones? Is a better one that will solve my problem? A God algorithm that will actually do it for me? Or is a better algorithm something that does it in less time? Because if I manage to turn off the recursion depth thing, which you can do totally, and just left it for like 5 years, it would almost certainly have the right answer for me on those 2 massive numbers that I spammed out earlier. So maybe it's all about the time taken or something like that. So we're going to be going into more depth about what it means to compare algorithms in a future session. But anyway, we've got 9 minutes left and we've got 1 slide left, so that's a pretty good balance in my opinion. So I am going to now be looking at, I feel like this, I've tried to make it a little interactive, but I feel like it could use a little more interactivity. So we're going to be using this website. It's New Zealand homegrown and very cool. So it's the NZOI group. I should not be signed in, I'll sign out. It's the NZOI group. So NZOI is like an acronym for this one New Zealand organization that does like some cool competitions, if you're ever interested in those, but I'm not here to advertise for them, though they are very cool. I'm here to tell you about how you can use this website because it's freely available online. So you might need to make an account, but all these things you can do without an account. And so actually, I'm just going to do it with these ones without an account. If you do decide to make an account, it takes like 5 minutes, and then you can look at a lot of past problems where you will be applying the concepts used in this slideshow and just the underlying ideas to make your own algorithms to solve problems. So basically the way it works is you will go to the website. You go to the website, I'll post it in the Discord later. You will go to the website, and once you are there, you will find a problem that you like. For example, this one. You go to the problem, and to submit, it will actually force you to make an account. That sucks. They shouldn't do that. It's proprietary software, that is. So I do actually happen to have an account, which is good. So I will go the problem. And the way that you do this is they give you a problem here. So the problem is like a bunch of lines, and then it tells you the input specifications. If you don't know how to code, by the way, disregard all of this. But I highly suggest learning how to code because it is a very, very useful skill. And it will help you a lot in actually implementing the algorithms that you will learn in this course. Because you will learn a lot of algorithms. And it's useful to know how to write them down in a way that is not flowcharts. You can still do them in flowcharts, but it is useful to be able to not do that. So anyway, if you do know how to code, then this is for you. So what you do is you go to the website. It will give you like the input specifications. You can use any coding language, including, I think, yes, you can use JavaScript. You can use both Java and JavaScript. You can also use Python, C++. You can use all the languages. Basically, the way you do it is it's pretty intuitive. You take the input, you find what output you got to give. They give you some samples to test your code. Then you go to submit, and you type stuff in. So I think I made this one previously for the session. The way it works is just you go to submit, and you press Control V, and you submit. You see if it works. You reload the page, you do it again, do it again, do it again, and do it again. And hopefully you do that. If not, that's fine. You just do it again. It is a little like the Otago math competition, but it's more focused on computer science and applying algorithmic concepts. Yeah, so here does Otago math. It's interesting. I feel like there might be a lot of overlap. I don't either. I have no idea what she's talking about, but I feel like that's accurate. Oh, that is not good. In fact, yes, just to help with the people who are thinking or who might agree with that statement, my poor brain cannot comprehend all of this knowledge. Let us go quickly through the slides one more time. Pixelated me. Right. The definition of an algorithm is just something that you do to attain an outcome, and you do it in steps. The history of an algorithm. 4 very cool people. Did a lot of stuff to advance our conception of an algorithm as we know it. One very simple algorithm where you find the biggest number in a collection of numbers. For example, if you had 3, 5, 7, 2, 15, 1, the biggest number would be 15. That was the biggest number I said so far, and this algorithm would help you do it. Oh, yes, I should also mention that you have no homework. I'm not going to waste your time. It sucks. People who said homework just suck, man. And no one's going to do it anyway. Let me tell you something. I'm a year 13 and I've never done homework in my entire life. I just don't do it. It's a waste of your time. Anyway, we keep going through this. Maybe I'm not a good role model. Disregard that, actually. That's kind of a bad role model thing to say. Anyway, but going back through this. Oh, no. Going back through this, we find the largest element in a collection by running through the whole collection and seeing what the biggest element was. But what's more important than this algorithm, which is kind of just made to prove a point, is the underlying ideas, that it was written out as a sequence of instructions, like we saw back here with the Kraft mac and cheese, and some inputs weren't allowed to it. For example, the pictured box of strawberries is not a collection that you can find the largest element of in the typical definition of largest as biggest number. I suppose you could find the biggest strawberry by volume or by weight or whatever, but getting off topic. And we use loops and indicator variables, 2 different very cool programming things. That's just a little extra for experts there. The Euclids algorithm, it's more mathematical and more complicated and a lot better for demonstration, I believe. So it finds the GCD of some numbers by performing these steps. And it works because of some underlying math. So here, again, was written as a sequence of instructions, use theoretical math to make it all work out. Some inputs, again, were not allowed. Algorithms can only take some inputs, and other times they will just fall apart. But if you give them the right algorithm inputs, they will work like a charm. And finally, recursion, and this idea of making sure that a recursion will stop if you are using recursion. It can be a tricky beast. It can go on forever. It can even do, well, I closed the window now, but it can even do what it did to me before and give me a lot of red text on my screen. And that's when it errored out. Some algorithms all around us: stock market, maps, Instagram, and Google. Those are some of the more well-known ones, but they're all around us all the time. Even the more prosaic occurrences of them, they're all around us. And a couple of ways that we can display algorithms if we want to look at an algorithm. It's easy to talk about one, but you might get a little lost in the word salad. So a better way to write it out is like this, for example, a flowchart, or like this even, a programming language that you can run on your own computer and put in whatever inputs you want. And finally, this website is pretty cool. So it's a NZY training website. Favorite teacher award. That's not good. I should not be your favorite teacher if you're not doing my homework. Yeah, this is not good. So this website, very useful. There's a lot of practice problems there if you want to practice like taking these concepts of writing out an algorithm as a series of steps. If you want to like go on a website that gives you green colors and congratulates you for stuff, and then you might want to go check out the website. It can be useful. Right now, this bar is covering my website. Very unfortunate. So I'll just do this. You can go to this website. For example, in fact, what I am going to do is I'm going to apply this right now. But you might also notice if you look at the time in the bottom right or bottom left or whatever it may be of your screen, it is currently 7:59. 7:59 is a bit of a problem. I will say that. So, anyone who needs to go now, yeah. In fact, that's an excellent song. No, I was about to play that song. That's not a good idea. It will probably like glitch out my audio or something. But yeah, it's the final countdown, and the thing is about to end. So I'm going to actually just stick around and try to apply these principles to create an answer for this question, because it's a pretty easy question from this year's NZIC round 1, and might as well try. But if you got somewhere to be, and I know a lot of you do, by all means, have a nice night. Nice talking to you, and maybe see you again next week if you decide to come back. So yeah, feel free to take your leave if that is what you want. What school do I go to? I go to Burnside High School. Oh, thank you, Hazel. You're too nice. Have a nice night. If you want, but if you want to stick around, I will go into this. We'll see who does stick around and who doesn't, which is fine. Have a nice night, everyone. Oh, thank you. How long will it be? I don't know. Leave anytime you want. I'll probably just like do it for 5 minutes because I've already got all the code written up. Homework. Homework is important. I know I said literally minutes ago that homework was not important. Homework is important. Do homework. For real. Okay, 14 people seem to be sticking around and want to see this. Bye. Enjoy your shower. Yeah. Okay. 5 minutes. We're gonna quickly solve this problem. So I'll close out the chat now. Anyone who's still around, this is what we're gonna do for the next 5 minutes of your life. Entertaining. Hannah's got a flower garden. It's a row of flowers, N of them, where N is presumably some number. All the flowers are red, green, or blue. That's nice. Colorful flower garden. And she wants to replace them so that they don't share the same color. So if she has like green, red, red, blue, that's bad. If she has green, red, blue, red, that's fine. And I can see why, because like you don't want your flower garden to look like patchy, you know? You want it to look like diverse and mixed up, which looks a lot better on the eye. So we can swap flowers for other flowers. And the way that we're going to do it is we're going to find the minimum number of replacements that we need to make a good flower garden. Okay, that's pretty good. Let's open up a notepad real quick. For example, if we had RGGB, well, actually, they even give us a sample case. First sample case they give us is RRR. And of course, if we just swap the middle thing for anything, say RBR, then we're now got a Good flower garden. That's nice to hear. In the second one, it's a little more complicated. They give us RGGBB, and notice that the sample cases are down here, RGGBB. So this is a little bit more complicated. I suppose what we could do is like RG, make this an R, and then this can stay a B, there's no problem there, but then this next one does have to change, and it will become, say, a G. Now this is good. We made two swaps. We swapped the G to an R, and we swapped the B to a G. So the answer here is 2, and yeah, it was actually 2. Okay, so I think we understand the problem pretty well now. Evie, I worry for you, man. I worry that you are not going to like your flower garden after you run it over, man. I mean, maybe you will. Maybe you will. Who am I to tell you how to do your gardening? I'm not a landscape artist. So, anyway, we are going to be given an input in. Oh, no, they all died. I'll delete all this from my code thing. We're going to be given an input in. So the way that we do this in Python is this. You don't really need to understand the Python that I'm writing down, just the ideas. And if you even just sound it out, in equals int input. So it's an integer input. The int is for integer, but people don't want to have to type out integer every time. So, and the next thing is going to be a string of length in. So I'm going to call that flower garden equals input. So it's an input. I'm not sure why in is really that useful. We're probably not going to need it. Anyway, so I think I've got an idea for an algorithm here. But first, let's see. Who's got an idea for an algorithm? Anyone? An algorithm that we could use to solve this problem. Not the code, just the ideas underlying it. So basically all this is you're given a string, and any time that you see more than one of the colors touching, you want to change that. You want to smash them all up. In my idea, if GG. This is, by the way, I feel like I should explain. This is a reasonably easy question. Not all the questions on here will be this easy. But yeah, it is pretty much as easy as our proctor has just said. So we're going to whip out exactly 2 colors. And that's important. This idea that in anything, say we have X, Y, Z, and we want to change this Y, and we want to take this thing and make it something that isn't the same, we will always have a way to do that. It's only touching 2 colors, and we have a palette of 3 colors to make available. So we'll always be able to just make a swap without needing to worry about any consequences down the line. The idea here is called a greedy algorithm. We make the best, most optimal thing at each turn, and we're just happy. So in this case, the way that I'm going to do this is, say I'm given a string of like, we're going to go through, we're going to start at the very start, and we're going to put this in an indicator variable. Who remembers that from the start? Like a little notepad thing. I'm going to put it down in an indicator variable, whatever that color was. If the next color is the same, and we're just going to keep going. Every time that we see a new color, we swap it into the indicator variable. And if the color that we see is either the same as the indicator variable, we just change it, and we add 1 to the number of changes that we had to do. And because we could change it to anything we want, it doesn't actually matter what the next thing is. So the color we change it to will be like X or something, not a real color. Because the colors are RGB, we're going to make it like X. So with all that in our ideas, let's make our indicator. It's going to be called previous flower equals, and right now it's going to be the first flower. Actually, no, right now it's going to start off as an X because there was no previous flower. We start at the very left and we're going to move through. So we've got our previous flower being X. It's unknown. And now for flower in flower garden. So this is the way that you loop through. Again, notice we're using another concept. That's why I chose this problem. We're using an indicator variable, which is going to be changed throughout the concept, throughout the code. We're using a loop. For each and every flower in this flower garden, moving from left to right, that's what this line means. What we're going to do is, if this flower is the same as the previous flower, then we got a problem. So but it's fine. I'm going to make a little other indicator variable type thing. Just this one's not really an indicator variable so much as a tally of how many things we needed to change. Right now we need to change nothing, and hopefully it'll stay that way, because that's minimal work for us, gardening. But maybe, well, Hannah really, but maybe Hannah might have to change a couple things. So if the flower was the same as the previous flower, we'll make the tally increase. tally equals tally plus 1. That's the way that you make something. In fact, the way that you make it is plus equals 1. Don't want any contradictions here. People thinking that a number can equal to one more than itself. That will be a bit confusing. And now the previous flower is going to go back to being an X because we know that whatever the next color is, it doesn't matter what the next color is. We can always just change this middle color retroactively to be something that fits with the next color, so we don't have to change that too, and the next one after that, and so forth. So we'll just make the previous flower be the X. Otherwise, we'll just make the previous flower into our new flower. Like if the flowers weren't the same, we're happy, we're fine. There's no problems. Now what we're going to do is print the tally. Now let's see if this works, because it might not. I'm not too good at code. I'm not too good at code. So 3 triple R, 1. That was what they said. No problems here. A little more complicated. 5, 2. That was also what they said. I remember that. So let's just go ahead and check. Are we correct? No hands. Hands off. Okay, reloading the page. Okay, and we did it. And I want everyone to notice what principles we applied here. We made this idea that we could use a little theoretical underpinning, and the theoretical underpinning was this idea that if we have 2 colors, X and Y, we can always make the middle color whatever we want in such a way as not having to change X or Y. So for example, if we had R and G, we can make the middle one a B, and we would not have to change anything else. So then we realized that we could use that to apply a greedy algorithm, which just does whatever it wants at each time and just moves through without worrying about making problems that might affect it in the future. Sometimes greedy algorithms don't work, and we'll look into that more in future sessions. But anyway, seems to have worked quite well for us. And notice we also used an indicator variable and a tally. The tally isn't really an indicator variable, but we use this idea of previous flower, this indicator variable, to write down what the previous flower was. And if the previous flower is red, we'll write it as an R. And if the previous flower was green, it'll be a G. And if the previous flower was the same as the flower before that, it'll be an X, because we can make that middle flower whatever we want. And finally, we used the idea of a loop. We didn't use recursion in this question, but I tried to include everything I could. And look at that, we got a lot of green on our screen. I think this is good. Good place to end off. I'll be seeing you all around. Bye. Have a nice night, everybody. Thank you.